We're very fortunate today to have a presentation from Professor David Alan Grier, who's Professor of Science and Technology Policy at George Washington University in Washington, D.C.
That's not good. Okay. I'm just turning it on to get ready. No remark upon what you were saying. Although get over the details about me. They're really
All right, well, very quick. With a particular interest in policy regarding digital technology and professional societies, and he was president of the IEEE's Computer Society in 2013. The title of Professor Grier's presentation is, well, it was Structured Software and the Break with Electrical Engineers. But now, it's this.
much more boring. This is not working.
It's not.
No, this is bad. I'm not an electrical engineer, but I can tell.
Frankly, I think it will add enough, aren't you?
Well, there's sort of a question. Mary, where are you? Can you hear me? Okay. How about the rest of you?
Yep.
All right. Yes. All right. Well, we're going to do it. Yeah, it was entitled, thank you for having me. I'm very pleased to be here. And I feel this is an absolutely wonderful room to have a talk in. Certainly about history ideas and the idea, so much of my research is going through a library and seeing an old binding and pulling it out and saying, oh my goodness, this is something interesting. It means you wander through a lot of things, but you live a most blessed life in the process. What I'm talking about today resides on one of my fundamental principles of life, which is there is no such thing as the physical reality of hardware. I'm a software person and have been so since a child. My father was in computing. He worked for the Early Burroughs Corporation. He took me to the office on Saturdays. He taught me to program. I had some wonderful times with him. And one day, when quite young, I learned that if you made a little mistake in the print statement that I was learning to program, this was Fortran 4 or Fortran 2 or something like that. Doesn't really matter. I wasn't really very good at it either. That it would print one character on one page of the paper and throw it out. And then the next one would go. And for the 10-year-old male mind, this is like the best thing in the world. It also got me banned, but it said software. That's where it is. So that's the first part of the story of why we're doing this. I've been telling people this is not as boring a talk as the title makes it sound. The second part is that this, in many ways, has its foundation in ideas that the Princeton historian Mike Mahoney used to talk about before his passing. And it led me to consider a broader context. We had several discussions about it. I'm willing to give him all the credit but none of the blame, if that's fair, for it. It got me thinking in new ways about how you center the world of computing and how quick, and I was the editor of the Annals, the Computer History Journal for 4 years, how quick we are to draw a tight little box around ourselves and say we're interested in that, because that is so interesting, how that machine worked, how that memory worked. And I know you're all involved in it, and I know that you feel the excitement, and I understand that. But this work is in a much broader context, and I think one of the aspects of looking at software engineering, which is of course the process, broadly defined, of trying to produce big, complex systems and do so in a way that's efficient, that's cost effective, and as we know, either has a minimum number of bugs or makes it relatively easy to find those bugs, is a difficult problem that expands your world and it takes you out very, very quickly. And so, turning off the microphone, you can also turn off this thing too. Does this have an on-off switch? No, that's on.
It's a hardware problem.
It's a hardware problem. So I have to go back and forth. All right. Oh, of course it doesn't work. This is my computer. As I said, it's all software. There we are. So the basic thing I say about this talk is it's not as boring as it sounds like it's going to be. Because it deals with a very interesting question. Exactly what are we engineering? And I'm part of the history of computing community. I've been on the listservs and discussions. And that question, real academic historians love to discuss, and they will love to discuss it for years to come. We don't have to worry about the unemployment of academic historians for many, many years, because they'll be talking about this. But some of the answers to it help us understand modernity and the modern age a lot better. So that's where we're starting. And not only is it boring, it's the great thing that I love, especially since I've been president of the IEEE Computer Society, the Institute for Electrical Electronic Engineers. I've loved using this phrase. Software engineering has no relationship to hardware. They get over that. And then I say, and it derives nothing from electrical engineering. And then watch them hit the wall. And that's just so much fun. But why it's not related is an interesting question. And the other piece that comes out of the story that I like is it's really tightly connected, the development of it, the modern development, to one of the great rivalries of the second half of the 20th century, which is the US-Japanese rivalry that flourished from 78 to 92 to roughly at the time Japan floated the yen and its economy tanked. And how it fits into that is also an interesting story, because it's the story of ideas. And computing as a discipline, hardware, software, any part of what you do, has been an amazing discipline to incorporate other people's ideas. We start out with it being mathematics, and computing is mathematics, mathematics is computing, but the modern computing machines involved, and I say modern here meaning, 1947. Modern computing, I'm a historian, there we go, involves logic, so it now involves logic, and then language, and then algorithms, and then graphics. We have been amazingly rapacious in assimilating other people's ideas, and more to the point, thinking that we invented them. And because of that, that picture of how we incorporate others' ideas and what causes us to do so helps us understand our time, our life, and most importantly, our technology. Now, Martin and I were talking about designers and computing. One of my interests in computing are marketing photos. And there are only about five generalities of marketing photos, 5 categories. One is guys holding up stuff. There's another one, guys pointing at stuff that doesn't mean anything. They're very different drawings. Guys pointing at stuff that doesn't mean anything. You see a guy, suit, tie, staring over something, pointing either at a printout or at some piece of electronics. It means nothing. But it helps sell it. So we started in '46 with guys holding up stuff. You see the Steve Jobs, that's a more modern guy holding up stuff. This, I should also say, this kind of photograph differs distinctly from the second major form of it, which is women pretending to do stuff. Women pretending to do stuff usually involves them wearing blouses and other things that really wouldn't work in an air-conditioned room. But it's there to show off the equipment and what it does. But it never gets at, none of these photographs never get at what it does, how you get it to do things. And we know that initially people kind of looked over that, but very quickly. There's Morris Wilks, for example, has a lovely little discussion where he's running back and forth to his computer room, and it dawns on him that he's going to be spending more time doing that than designing the next computer. And he's not the only one who came up with that. How do you make it work? This is a graph that Herman Goldstein, who will figure heavily in this, came up with, which he thought was the best thing in the world for simplifying the complexity. You see some of it. This is a diagram that dates to about 48 of how he was thinking of dealing with mathematics. Because to him, he was a mathematician. Computers were about mathematics. You write down the equation, partial differential equation, and you're done, mostly. He's enough of a mathematician to know you're not done completely, but you apply an algorithm and you're done. And then he discovers that there are conditional statements, if then else. And then he begins to realize complexity is getting harder and harder, and he doesn't know how to handle it. Well, if you want to look at people trying to systematize programming, you start with Babbage in the 1830s. I'm in England, so I probably don't need to explain to you that Babbage had 2 distinct designs which clearly merge one into the other. One is not really programmable in our modern sense, the difference engine, which last time I was here, there was one over yonder someplace. Still there? Nice to know some things are fixed. But he had another one which was programmable, and the fascinating things about going through his efforts at it was recognizing that he didn't quite know how to do it, and that he's learning it, and he, of all people, has no one to help him. And so he's working out various forms of systematizing. This is from the famous note on the difference engine with Ada Lovelace's contributions. Trying to figure out a systematic way to describe it, to break it in parts and make it work. And one of the themes of Babbage that I have liked that I think gets lost in his life, and because we get so fascinated with the gears and with the machine, was that he defined himself as an analytic. He was the founder of the Analytical Club at Analytical Society. He was using that particularly in reference to a certain form of calculus at the time. But you begin seeing that particularly in his economy of machines and manufacture. He loves breaking things apart. He loves dividing it up and trying to figure out order. And that's the exact skills that he's doing there. And that in many ways is the foundational skill of software engineering. We can go on, and clearly Zuse had it in the 1940s. So we're jumping 110 years in a wink of an eye, and then breaking historical narrative lines. I'm then going to backtrack to 1910. You look like a sophisticated audience, and I can trust you. Zuse clearly is working out these things. He has a very graphical way of doing it that in some ways looks like a spreadsheet. His work was unknown outside of Germany until after the war. And so its initial impact is not as great as it might have been otherwise. But the person who does do much of the fundamental organization is this man. This is Hermann Goldstein. He is one of the guys holding stuff in that first picture. Goldstein, University of Chicago, PhD in mathematics, taught at the University of Michigan. During the Second World War, gets drafted. He volunteers for the Army, for ballistic service, because he had worked his PhD work under one of the mathematicians who had worked in the First World War and understood the kind of systems of partial differential equations that ballistics requires. So he volunteered, and it was great. He meets John von Neumann, and as far as I interpret his life, at that moment in his life, he got one goal and he fixated on it for the rest of his life, or until 1957, which was to be John von Neumann's best friend and assistant. If von Neumann needed it done, he would do it. If there was something that needed to be written up, he would write it up. The classic draft report on the ENVAC, the first computer to follow the ENIAC, it took a while to get going, and the ENVAC snuck in, and a bunch of others. But the one that kind of started the process towards our modern computer, the original manuscript's in the Library of Congress. You get to it, you open it, it's in plastic, it's very nice, you have gloves on, you're touching it gingerly, and you notice that the handwriting is not John von Neumann's, because it's Hermann Goldstein's. He, in starting to set up a computer for von Neumann, had no idea where to begin. And he turned to manufacturing engineering rather than electrical engineering. He's a mathematician. His concepts of electricity were quite similar to mine in that you are willing to stipulate that electricity exists in a theoretical concept, and that it might or might not have certain properties that follow equations, which we like. So since the equations work, therefore we can conclude electricity works. So that was his relation to electricity. He drew program, and there were several people around him that drew it from other sources as well, primarily from production engineering. When you are a plant manager, a plant engineer, you would do a program of daily production, a program of monthly production. You would have a progression sheet, which he also played with for a little bit. Progression sheet being how much work got done today, what needed to be done tomorrow. And so looking at the literature, we see the first grasp of where you're going to find ideas. Now, as I said, there was no connection at all to electrical engineering. Howard Aiken was working with some of the same ideas, and his computer right here was, for the most part, mechanical or technically electromechanical. Zuse's computer was also mechanical. And electrical engineering was working on ideas that get pulled in later. This is where my statement has no relation to electrical engineering gets a little hyperbolic. Because the key idea in electrical engineering in the late 30s and early 40s is black boxing. Getting a circuit, a complex circuit, so that that's the circuit, there's an input, there's an output. What goes on doesn't matter. There are several German engineers who were the leaders on it. Americans start picking it up in 41 and 42. I'm not sure of the UK history, but I would guess some compromise between the two. Head of Americans after the Germans. and particularly filter design is where it comes from. But that doesn't come back into computer and software engineering for another 30 years. What's going on at the time is figuring out how you make it work, and so you turn to factories and factory structures. This at the time is the most sophisticated factory of 1947. It's the River Rouge plant in Ford, that Ford owns in Detroit. And that production process was the most studied in the world, and it particularly emphasized the idea of linear progression and dividing complicated structures down into small steps that could be handled piece by piece. It was a very brittle form of engineering. You got it right, you held your breath, and you ran your assembly line until it's done. Now, my colleagues here who know my work and have heard me talk before know that I will never give a talk without this slide, ever in my career. Certainly, Martin and Mary know this, and they have teased me about it shamelessly. This is the finest of all computing groups that have ever worked on the planet, the largest and most powerful prior to the creation of the electronic computer. This is the Math Tables Project. 450 people, and the photograph is very impressive because they just go on forever. Doing calculations of higher mathematical functions using paper and pencil and nothing else. There are a couple adding machines. Those are the people who are double-checking results. This group had a problem. And in setting up this operation to do the calculations, they directly again turned to factories. How do you control the flow of paperwork? How do you control the project from the start to the finish? How do you check for quality? And the founders of it directly worked with plant managers, particularly that of William Henry Leffingwell, to figure out how you broke up calculation in a way that those people could do it. This is, of course, kind of the golden age of production engineering. And I list these 5 names because in some ways, these are the 5 that in the 1950s, their ideas are being referenced directly in the writings on software development and software engineering. And one of the things that helps, and this is where being the president of the IEEE Computer Society helps a great deal, because when they talk about history, when a professional society talks about history, what they mean are celebration of past presidents or other famous works. This person was here back in 1971 and they were a genius and we celebrate their contributions. What they often miss are the obvious trends of thought that underlie what they do. And in 1950, the IEEE began the first and what's now the longest continuously published journal on computing, which is called the IEEE Journal on Computing. And at the same time, just a year or 18 months earlier, knowing how the IEEE worked, probably 18 months, they bought a UK production engineering journal and put it into their mix so that their members could get both. So you're seeing these ideas at some level move into the engineering community at roughly the same time. Now, Ford, without question, is the most influential manufacturing engineer of the 20th century. In particular, his idea of ordering steps, simplifying processes, unifying a product so you get a flow. He did not write extensively because he was a businessman, much the way Bill Gates is, but his engineers did. And their writings, which are largely in this IEEE journal, explain how they did it, and they were particularly interested in information flow. You've got a car going up a line, what information does it have to carry with it? And how does it move back? And Ford famously said you can have any car color you want so long as it's black. That applies to one model. That's the Model T. And the Model T gets replaced by the Model A in 1928. And he, at that point, realized that to compete with General Motors, you had to have options. And he loathed options because it meant other colors than black. And that meant an information flow. And so how do you engineer that information flow? How do you break it across, carry it forward, and make sure that it is conglomerated in the right way at the end? One of the people who helped him with it is Henry Gantt. And I suspect almost everyone here has done project management and know there are things called Gantt charts, but don't know there's a guy named Henry Gantt. He is a bit of a character himself, but in particular, he looked for ways of graphical representations. This is one, and this is the one closest to his common form. But you go back to his 3 books, and you can see him working out the ideas. How do you track information flow? What do you need to know on what step of the process to understand what you need to do on the next step? Following Gantt, we can see Goldstein turning to Frederick Winslow Taylor, who after Ford is the most influential production engineer. And he was particularly interested in optimization. In the idea of optimization, he worked in fairly simple problems, largely machining of steel. And his idea was you break every motion apart in the machining of a steel process, study it, figure out the optimal one, reassemble it into the whole, and you pay workers by the piece, and then the whole combination is the most efficient way of working. His work was highly controversial, and most people who claim to be Taylorists actually have developed other techniques than what he presented. But he let an idea go, and that analysis, that optimization, and that looking for the right set of ideas, right way of doing it. He had a phrase, there's one right way, which is not true. But he promoted it, and that idea took a certain amount of hold. My favorite one in the literature are these two, Frank and Lillian Gilbert. You may be familiar, there's a children's book called Cheaper by the Dozen, which if you have children, or judging by some of the faces, perhaps grandchildren, who saw a recent movie starring Steve Martin, that movie has nothing to do with the book, absolutely nothing. Frank and Lillian Gilbert were production engineers. Frank Gilbert got his start in bricklaying. Lillian Gilbert got it largely by being with Frank Gilbert. She was an undergraduate student at Vassar and did more liberal arts things, but became a force in her own right. Their major contribution was recognizing not that you take pieces apart, but you identify what each piece is. In a production process, it's not only the pieces you're making, but the motions, how you hold something, where your hand goes. And they invented a language, which is called the Thurberlese, which is Gilbert spelled backwards. That was a language for describing production. And Lillian Gilbert wrote a number of articles on it, and they had a certain number of students, and it fizzled out eventually because it lacked all the things we know a good programming language should have. It should have unique ways of describing things. It should be uniform against various forms of translation. It should have ways that are the most efficient ways of doing activities. And there you had multiple ways of describing it. It was a very sloppy design. But that too got merged into the literature, and people talked about it through the 50s, and it was re-accessed as people started to look at software problems. Now, if you look at this journal, the Institution of Production Engineers, this is the journal the IEEE bought. It gets started in 1922, and its real heyday, the great articles in it, are the 20s and 30s. One of the great pieces of attitude was that the world was completely knowable. You could basically figure out everything you needed to know, and if you got enough detail of a problem, you could solve the problem. So it's very much a rational, positivist point of view that too gets incorporated into early software engineering. That if you know enough, you can make it happen. The one thing that gets in the way was a few articles, largely published by the followers of Samuel Insull, that there's limits to knowledge. And in fact, not only are there limits to knowledge, at some level, looking for those limits helps you understand a problem and aggregate information in ways that prove to be more useful than if you know everything. Insull ran electrical utilities. So here I have to confess that perhaps we have a thing called an electrical utility that obeys mathematical equations, and that perhaps it provides electricity to places like here. What he figured out was that you could see patterns in aggregation, and that by bringing more people into a utility, those patterns would smooth out into these smooth curves. You could predict how much you had to generate, you could do it minimally, and you could make adjustments during the day. That allowed him to write a series of tracts to his followers on managing for the collective experience, not managing just for one household. And before him, people had thought you had a generator, transmission line, one household, and they're trying to solve that problem. And Insull was saying we solve it for the community because the average experience is more interesting than the individual. And this leads us to who is probably the founder of software engineering, Walter Schuhart, a man who's wrote 2 books, and that's it, whose writings are a challenge for the expert to read, and I suspect for non-experts beyond readable. His first book is in 1931. He wrote it when he was an AT&T production engineer. AT&T had a motto that was called one service, one unified service anywhere in the United States. That the phone would operate the same way, that the phone set would be the same kind of set. The engineering you did locally in New York City would be the same that you did in Los Angeles. And in particular, as long distance lines, which are just, the first ones are coming out in 1914, but it's really 1921, 22 before you get real quality long distance lines and hence a national network. These long distance lines were really trying to pull it together and say we do have one phone system. Shewhart, reading the quantum theory and the other basic physics of his age, decided, and this is what makes his book so thoroughly unreadable, was that the world was unknowable, just as physics is ultimately unknowable. You can't know everything about the state and motion and energy of a particle. That was true about the world at large. So he decided he would come up with a mechanism for managing ignorance. He argues that it's easy enough to manage knowledge. What you need to do is manage and understand what you don't know. So these ideas start creeping into software in a very scattered form. One of the places, obviously, where they start collecting it is Herman Goldstein and the ENIAC and the John von Neumann machine. But the SAGE is where they start doing it in a systematic way. In some ways, the SAGE computer is the start of so much of computing. They wrote a series of routines for it, software for it, that helped Air Force officers track objects that are moving through airspace. And it's tough, looking at the software, it's tough to call it a real operating system because it wasn't. These various switches and buttons would allow you to call routines up very quickly, but there was no background system really running and holding it. There were, it's more like a collection of subroutines, really, that are processes that are sitting out there waiting to be called. It was the largest software project of the time, and the focus on it is primarily of producing unified code, of having a coding style manual, having standard ways of calling routines, standard ways of producing output, standard ways of looking at the code and engineering it. And they adopted many ideas from production engineering, and also, though, considered themselves engineering code. If you look at the manuals, they talk about how well the code is engineered. Well, they were a fairly influential group for much of the 50s. I'm going to use a term here, obviously, software crisis, that has currency in the community of people looking at software. It's a period from roughly 64 to 68. I'm not sure it's the right term for the age, but it points to what's going on in the social economic world. The IBM 360, which is shown here, is at some level one of those very first modern computers, and certainly the one of those early modern computers that has the largest installed base. It's released in April of 1964 and very quickly builds up that large base. At this point, IBM supplied a certain amount of software, but software was largely a local problem. If you ran a business, you'd buy it and you set up the software that you would need. And the crisis was the argument that there was an insufficient number of trained personnel, of trained programmers. This feeling lasts 64 to 72-ish, that there's just a demand that if you have any skill at all, you'll come in. They'll hire you. One of the stories that I have used several times is my very first boss got her start in 68 or 69. She was an undergraduate, she fell, broke her hip, lost her scholarship because she couldn't stay in continuous enrollment, and moved to New York to be a programmer. And she knew Fortran, she knew some COBOL, and she said walking into male bosses' offices and explaining what she knew and watching the look on their face going, I'm desperate for a programmer, this is a woman. What will I do with her? And she also talked about their working in offices where there were no women's bathrooms and other things, and how bosses often would contain their anxiety until some point and they would blow up. I also know she may or may not have been the easiest employee to have. But there was that feeling that there wasn't the personnel. And if you read, and there's a big discussion over this. The popular literature, like Datamation and the scholarly literature, part of the discussion is how do we train more people? How do we get a larger workforce? And in fact, the solution was probably quite different. It was probably how do we amortize software over more sites, the birth of the software engineer. But at this time, there's also a growing concern about the state of manufacture. Ralph Nader wrote a book, Unsafe at Any Speed, which was a critique of the designs, automotive designs of General Motors. 1967, of course, has the Apollo 1 mishap, where an Apollo capsule caught fire on the launch pad. And we are seeing an increasing questioning of the quality of engineering and how well it is serving the American public and the world. In the United States, during the later part of the 60s and the early part of the 70s, there's an increasing concern about Japan starting to enter into American markets. It starts in the late 60s in small items, cameras, adding machines. It builds to cars following the first oil crunch in 1973. And books like Ezra Vogel's Japan is #1, and in particular Theory Z, which is behind it, argued that Japan had managerial techniques and manufacturing techniques that were superior to those of the West. And the last book behind it, In Search of Excellence, which is Thomas Peters, one of the most influential managerial books of the period, is very much a response to that. And so you've got at this stage concern about the quality of manufacturing, concern about software, concern about what to do. And 1968 comes, and IBM announces that it had provided a lot of software for free, or bundled in with its software, with its hardware leases, and it's no longer going to do that. If you want software from IBM, you're going to have to purchase it separately. It did this, as were many of IBM's strategic decisions, to get ahead of an antitrust claim. But it also, in looking at their documents and looking at their story, it's clear that they are seeing software in a new light and are getting concerned that they are not as able to handle it as they were. And they think by unbundling it, they will free themselves from some of the software that they don't want to do. In particular, there's an early set of documents that talk about people being free to purchase software from the software vendor, which they mean IBM, or an outside software vendor, which they mean other people. And they viewed themselves still as central, but they thought in general it would be a positive thing. And that fall was also marked by the Garmisch Conference. Now, having worked with software engineers and been their public representative now for 2.5 years, one of the things I've learned about them is that Garmisch has, at some level, the same status. I'm hesitant to use the word Jerusalem, but let's work with that for a moment. It's not that it's a divided city that people are fighting over. It's this holy place where something great happened. And from there, software engineering came from. Kind of like the Ten Commandments on stuff. It's a much more complicated story. Garmisch represented a conference held in October '68 called the NATO Conference on Software, and it was concerned with software engineering. It coincides with IBM unbundling, but it seems to be a coincidence in that while the same forces may have produced both, one did not directly relate to the other. From the start, there's a debate about, do you engineer software? What there's not a debate about is how you produce, that the goals of the conference is to produce quality software at a low price. If you look through the discussion of it, the conference has fascinating things. There are big strategy things. There's small things. There's a discussion of how do you keep a notebook to manage your software project. It's everything in between grand ideas and little details. There are at least 2 and probably 3 major competing visions at that conference. The most prominent one was that of Edsger Dijkstra, who was the Dutch computer scientist. He argued for a thing called structural programming and formal methods. And I'll get to that in just a moment. There was at least one competing field for mechanical engineering, which was Douglas McElroy, who talked about the needs for the software components. And there were other various things about an empirical structure or a more adaptive one. They agreed to have another conference the following year, which happened in Rome. It was nowhere near as successful, and that strain of development kind of died out. But the notes from that first conference and the ideas it set forth quickly start pulling themselves together into software. Now, McElroy felt that there should be a components industry, that people should produce gears and bearings and axles and little pieces that we would all assemble in software. And his ideas keep getting reiterated in reusable software, software library, software lab. So it didn't exactly go away. But he argued quite strongly that this was the main thrust of it, and we needed to do this part first before we got to it. Well, in fact, by 1968, we had done. The ACM had a collection of algorithms, which were called the collection of algorithms of ACM. And they offered them to you free in some variation of Fortran. If you look at those things, they were critiqued heavily at the time for being badly coded. And indeed, there's some horrid coding that you look at it and you say, how do you get this in go-tos that flip it back and forth? And that they needed to be engineered better. They took a second stab at redoing them, and very quickly commercial firms started outdoing them, and they lost interest. But some of that had been there, and that wasn't really quite the foundation that we needed. Dijkstra has an interesting and I think slightly controversial role in computer science, but clearly he got in places where he threw bombs, the bombs broke up things, and allowed to go forward. His most famous is this letter. It's just a letter. Go-to statement considered harmful, which he wrote in the communications of the ACM. And he basically argued that the go-to was bad for your health. It set up a huge debate. And what happened is people largely followed, largely accepted the idea that complexity in coding was bad. But that didn't lead to his foundational arguments on what software engineering should be, because he too sort of argued that we're engineering the code. We're making the code look good. And some of you may have seen this. I don't see anyone, sometimes when I give a talk, there's this flashing light of, yes, I haven't seen that in 35 years. None of you are doing it to these diagrams on the right, which are his flowcharts representing these things. This was the conventional if-then-else of the 60s. He wanted to represent it that way. And his idea was that these things can be assembled in rectangles, and they get more and more complex, but there are rules you can use to parse the rectangles to prove their correctness, and then you code from the rectangles. And if you ever saw a flowchart of his for a complicated program in that rectangle form, and if you can make sense of it, you're smarter than it's a tough thing. But again, it was code engineering, that somehow that was the problem. Well, at this stage, it's clear that if the component industry is not going to do it, and engineering code is not going to do it, then a third part may be of some help, and that was standards development. And what happens is software engineering largely goes up this track. There are several that started coming out in the early 70s or even in the late 60s. The principal one, if I can skip ahead, there we go, were the National Bureau of Standards Federal Information Processing Standards. And of course, when I mean principal ones, I mean over there. I'm sure they pale in comparison to anything done in the UK. Not as important, not as widely circulated, badly written, and there you are. But you can see what they're doing. 1968, standard code for perforated tape. 1969, standard 4, dates. And those are calendar dates. It should be noted that 1969 was the first year that had a significant problem with dates when the decade rolled from 69 to 70. And you wonder why they didn't figure it out for 30 years later. Hollerith punched card code, flowcharts, COBOL conversion. They are still looking fairly low level, still looking at small problems, but they are getting the community used to thinking about how you represent things in a standardized form. These go very quickly in the early 70s to looking at bigger issues. And it's these bigger issues that really get it started. The US military standard 1679, software development standards. This is mostly how you run a project. It's at some level, specification standards and testing against the specification. And if you look at the academic journals at the time, including those, bless its heart, the IEEE Transactions on Computing, they run a short article entitled, "Why Bad Software Can Often Be Good." And the author talked about how, sometimes what you would expect the result to be is not the one that most people want, and so you want the incorrect result because that's more useful. And that elicited an acid-tongued, I think is the right way to reply to that article going, what the author has just described are specification standards. And what he is saying is that if you set the specification to do it this way, then that should be the result, even if human logic tells us that's wrong. And what that process is indeed correct. So that's the Military Standard 1679. Guide for Documentation, 76. And the real start of it is IEEE 730, which once you get there, we are getting a sense of what needs to be engineered. The issue is quality assurance. That is becoming a more prevalent topic in the 70s as the students and friends of Walter Schuhart start promoting it, most notably W. Edwards Deming. But Giron and others are publishing books on how to do quality assurance for manufacturing. And how do you put together a plan? How do you adapt that to software? Comes out in that 1969 standard. It's 1979 standard. First systematic work on it was done in 78. And it was a group of engineers that said, we need just a strategy. We need to think about how do we approach it. They never really intended that this was going to be software engineering or a major part of it. But they were recognizing that this was the theme of the moment, that this is what manufacturing engineers were thinking of, and that they needed to respond to it. From that follows a series of roughly 10, and these are the 7 probably most visible ones, that deal with it and directly go back and reference 730. They start with test documentation, because once you have a plan for software quality assurance, you have to test it and document the tests. Well, once you did that, you realize that we start needing to think about specifications more systematically and have languages and structures for it. We needed a taxonomy of software standards. What did we want to have to make software good? We revisit the quality assurance 730 a decade later and update it in light of all of those. There's a certain lovely little situational irony in that. We then come up with measures. What can we measure off software? How do you manage a configuration, which is beyond it? And finally, in 1991, we get 1074, which at some level puts all of this into structure. That the basic idea is a thing called the software lifecycle, and that we are having to manage for that software lifecycle. The idea of the software lifecycle comes from Schuhart. This is Schuhart's original diagram in his 1931 paper. We now know it in management as the cycle of continuous improvement. And it basically starts in this part here where you specify your software, in our case, or your manufacturing process. You build it, you test it, and then you go around the circle, always looking for something to fix, to advance. He was doing this in a statistical form because he argued the world was unknowable. And that unknowability, which I mentioned earlier, had deep philosophical roots in it, but it became very practical in the hands of these early engineers. Because they argued that the world was knowable, they just didn't have enough money from their bosses to be able to do that. And in fact, one of the interesting things in working on this project, in 2004, I think it was, I was at in the Ukraine, more or less where they were having all the protests quite recently, for the centenary of Vasily Lebedev, the inventor of the first Soviet computer. And you sat with the engineers who were his students, the people who worked with him, and we were talking about what they did and taking interviews with them. And they complained bitterly about their bosses, how they didn't understand the technology. And if they'd only give them more money and more time, they could have really done something. As it was, they were only able to shoot down Gary Powers. And it brought sort of a new focus into that problem. but they accepted this idea that something was unknown that they would never get to know. And so they had to manage their ignorance and respond to whatever little detail they got to adjust for. By 1991, that cycle has become this, the software life cycle. You start with your requirement specification, design your system, you code it, debug it, install and configure it, operate it, finally assess what you have done, and go around the cycle again. And all of a sudden, instead of engineering a single piece of software or a single line of code, you now are dealing with a much broader set of operating procedures, a much broader set of activities, and it never stops. At the IEEE, this is one of my IEEE sales slides. I have been going around selling this. This is the software engineering body of knowledge. Just forgive me. I've just been around the world too many times in the last year. We started taking a look at the software life cycle 2 years after it comes out. We set up a coordinating committee to try and pull all these standards into one. It ends up being assembled in 1995. We get it as an international standard on the software life cycle. We release all this material as, we love acronyms, Software Engineering Body of Knowledge, SWEBOK, in 2002. And during my presidency, in the final days of it, I told them I would embarrass them no end if they didn't finish it. We got the 2008 version of it out in 2013, so we call it the 2013. This was basically developing the same thing, and by the time you get this document, I should say it's available freely on the web. You can download it, it's a PDF, it's lovely. Use it to teach your students, teach yourself, hand it out on the street. We're not engineering software anymore. We're engineering something bigger and beyond. Systems, processes, offices, data flow. All of this come as part of it because how you actually code it, we know it's useful to code in a disciplined way. It's useful to have common standards. But the real thing that you're engineering is something bigger and beyond that. And so just last week, it led, this is a question I've been dealing with all the past year when people say, well, why do you need to learn this? Why do you need to do this to code? Can't you just, you know, there's things on the web you can learn to code from. It does beg the question, what makes an engineer? In civil and electrical engineering, engineers who are involved in projects that involve lots of money and risk that can damage a lot of people and put those assets at risk, get a professional engineer certification, largely to make people lending money feel good. Last week, it was actually not 2 weeks ago, I was having a coffee with a former student and her husband, who was an anthropology major in college and is now the chief software architect for WordPress. It's not a big project, widely used though, working its way up the corporate ladder. Important, interesting number of lines of code. It's crossed over 1 million recently. And his knowledge has been gotten through very non-standard ways. Learning on the web, learning from friends, being part of this project and working his way up. But as we went through the body of knowledge, which his wife and my former student found incredibly valuable. So this isn't a famous fact. He knew all these pieces. He had learned about engineering the life cycle. He had learned about specifications. He knew about it and knew it at a fairly deep level. He had never taken a computer science course in his life. I come back as having a father in computer science, and I had been able to say that. But he didn't. And he has been learning it through this new way. And that led me back again to that question of what is being engineered. And I think that's the fundamental issue that we see in software engineering. We aren't just engineering code. That's long gone, although, as I said, standardized code, standardized processes are useful. We're not really engineering the standard computing environment because increasingly things are done on virtual machines. And instead of getting shipped a program, you get shipped a virtual machine, which after all is a program that simulates a certain kind of computer with running certain kinds of software. And that software has been set up in a way that works fairly efficiently no matter what's underneath it. But it's that bigger issue that's outside, the production process, the production of goods and services. I have another slide which is not part of this deck, which I go through the basic issues of modernity. And in this case, modernity in the standard sociological definition is industrialized production of goods and services, urbanization, and bureaucratized management. Bureaucratized, rule-based bureaucratic management. And I just start on the first one and say, what do we produce with industrial production? So we go food, we do clothing and cars and electronic devices. And I say, yes, but we also do food. And that usually gets them started. I noticed, I had lunch in the museum, and I got what I believe you call crisps, which I believe I call chips. And on it was brazenly written, made by farmers, which should be a little bit worrisome if it's made by elves and trees or something else. But the other fact is farmers are part of industrial production. We have industrial standards, industrial tools, industrial ways. There's more variability, but it too is an industrial production. And I have one slide that says we've now industrialized social life. Because what's Facebook? What are all these dating sites? Do men now actually have that experience, which I know every man in this room has had, of going up to a woman they vaguely know, are vaguely attracted to, and say, hi, do you want a cup of coffee? And I don't think the answer is yes, because they have ways of buffering them, making it easier, having a wider chance of success. And women, that same thing of looking over a guy, going, how do I tell him no? We don't have that anymore because we have Facebook to do that for us, or Twitter, or Instagram. But those are the processes going. And so when we're looking at the process of engineering, process of software engineering, it's really part of that bigger process of building an industrialized economy of urban life. It certainly is deeply involved in rule-based bureaucratic management. But that's the world in which we live. And when we look ahead right now, I think at some level, I appreciate what you do. I think the idea of keeping the artifacts of old computers going is important. To understand how it worked, how the people who operated and coded it spent their daily lives is important. We know very little about how the printers of Gutenberg worked, or the similar people who helped build the Renaissance and the Reformation and all that flowed out of that. We have a chance to capture sort of what the workers of this industry did in the work that you do. But I think the bigger work around it that we have to build on is how we have rethought everything in our lives, and how software engineering is part of that process of engineering what we do to produce goods and services and food and social life. And with that, I'm at the end of my slide deck. Invite comments and questions. You can ask questions, or in Martin's case, you can give a little speech and pretend it's a question.
Very good, thank you.
But you've seen most of this before.
I was interested in what you were saying about Goldstein and his knowledge of industrial process engineering. What kind of evidence do you have for that? I mean, did he have a collection of books, or did he cite the literature?
He cites the literature a little bit. This is like one of the questions I wished I'd asked him. I had one meeting with him back in 2004. Mostly words and phrases that he picks up and uses from time to time. He wrote 3 papers. This is insider. He wrote 3 papers with von Neumann and Burke and someone else. And really, he was the author of it. And you go through it and you'll grab little phrases that are common in the IEEE Journal of Production Engineering.
One of the reasons I ask is that when I tried to trace the term flow diagram, it took me back to chemical engineering, that is where it comes from. And von Neumann has an undergraduate degree in chemical engineering. And that's where I sort of presumed that that's where it was coming from.
But that's part of the same literature. So, because it becomes chemical engineering, and then that gets transferred into the production line work of Ford and others. So it clearly could have come either way. I'm not sure, I'm pretty sure he wasn't much of a student of it. I think he and the others at the time would read something and go, oh, that's how you do it. And
Yeah,
he's
and
run it.
it's one of the points that Mahoney makes, really, isn't it? That
This is
software
our-
engineers kind of they appeal to this idea of Fordism without ever actually knowing what it is. It's
Mhm.
just sort of voices in the air that they pick up.
And if you look at that journal, there are lots of references to Ford, and there are only a couple direct connections. And what they're basically referring to is analysis of production, breaking into small parts, and sequencing it, doing it so that it's done A, B, C, D in a certain order. And clearly, that's in the air, and clearly, how much of it Goldstein read is not clear to me, and I'm fairly sure it isn't much. But he knew the words, and he spoke them with a certain authority. Now, it may be Julian Bigelow, his engineer, but it's fairly well documented that he and Julian Bigelow started hating each other pretty early in their relationship and never got over it. There's a recent book by George Dyson about that. This is John von Neumann's first computer. And I think the one thing he has done is redeemed Julian Bigelow just a little bit. He needs to be redeemed because he made this thing work.
You mentioned Sage,
Yes.
but you didn't mention the word network anywhere in your
No.
presentation. Of course, Sage, I think, was one of the earliest networks,
Right.
which led on
Certainly
to...
distant communication. Sage was connected to radar, just for those of you
Correct,
who don't.
right.
Radar stations up in Canada.
But that led on to things like the American Airlines reservation
Sage.
system and all
Yeah,
the transaction
Sage.
processing, and eventually the internet,
Mm-hmm.
which flowed from that. And aren't we now developing a rather different view of systems and software that actually you can't engineer it any longer? You engineer pieces that then have some statistical collective behavior,
Mm-hmm.
which may be adaptive in ways that we don't understand. And the whole thing is by no means a specified and engineered artifact.
Well, I think that's why Schuhart's work has become so firmly ensconced as the foundational set of ideas for software engineering. Exactly right. That the people who, Sage is a network, isn't a network that we would recognize. It was phone lines going to radio station, and you didn't switch them. They came in, and that was it. That it adopts to situations that we don't foresee. His argument that the world was unknowable, software engineers fought through the mid-70s. And I think, just as you said, we now believe that. We believe that you never know how the system works. But we have a tool to optimize what we have control over. And that tool is based on the fundamental ideas of Walter Schuhart.
If I could just follow up on that. I
Sure,
mean,
you can.
the software life cycle has had a pretty good beating lately because it's not quick enough.
Mm-hmm.
But there is another fundamental flaw, which is that you can't write the specification first and then construct the software to implement that specification. By the time you finish doing that, the specification has already changed.
Mm-hmm.
And that seems to rather undermine the whole thing.
Undermine it or localize it. I mean, we are still clearly going in feedback loops.
Yes, I agree with that.
It does seem that we are developing sort of a Ptolemaic view of it, where you have the big cycle and you have little teeny epicycles in it. And Agile, in many ways, you've got one big swoop around with all these little things around it and how you collect it in.
Yeah.
But it's still this issue of dealing with uncertainty and how do we think about that uncertainty and build what we have control over, which is the software, to deal with that and deal with the larger system that's embedded.
I do agree with that. And I think most successful pieces of software have been through many iterations.
Oh, yeah.
Life cycle.
In this day and age?
And what we have, certainly in this country, I don't know about the US, is the usual government software failures, where they tend to do the whole thing in one cycle, and it never works.
I can't imagine that we went through one of those recently. The stories that pass around Washington about that failure was that they were trying to do a software life cycle push without any back iteration, and they were heading into testing 2 weeks out. And we all sit there staring, going, what could they have been thinking? But someone pitched that contract and someone bought it. Question back there? Yes. Yes.
If I was listening to your talk and I wasn't in the software business,
Excellent.
I would think you, if I wasn't, I think I would think I was listening to a rather successful discipline that had learned how to do things right, but a shamefully large number of projects still fail or never reach conclusion. Do you have any thoughts on why that is?
Because it's a messy, hard problem. And I should perhaps add that slide into the one I have on WordPress. I find it fascinating that so many projects successful projects are done by what members of the Computer Society consider to be amateurs. And we have things like the Obama healthcare site, which was done by a very successful software contractor, which was awful. And I don't know how much they spent to fix it, but it was a lot. I think it measures, Matt sort of points to two things. One is the ultimate difficulty of this field. And second, that problem of drawing the box. I did not incorporate the idea of black boxing, which is a software engineering that David Parnassen introduced into software 74, 75, something like that. We have borrowed a lot of things, but one of the things of engineering is I said, you find where you draw the box. And once you do it, you've got to understand everything in the box and the input and outputs work. That is a useful tool, but not the only tool. But in software, there is a sense of where do you define the boundaries of the system. There's input data and output data you have to account for at some level. There's some sense of human behavior that you have to grasp. And understanding where you draw that is tough. The recent Mt. Gox failure, I too am a student failure as well. This is the Bitcoin failure that the Japanese got robbed. Inside or outside, I'm not sure I care. I was really fascinated with the technique, which exploited a delay in communication that forced the software to set up a temporary, unverifiable number. And I'm sitting there like going, this is the stupidest idea I've ever heard. Why did they think that was good? Because they thought that they could keep that inside the box. They didn't need to worry about that. And in fact, it was something outside they could. So it's hard, and it involves this idea of what's the right place to cut? What do you include? And discipline within what do you defend against because you can't?
Thank you.
Sure.
Oh, sorry.
Yeah.
One of the interesting things in my experience is that some of the best people at handling software problems didn't actually have a background in computing or mathematics or anything to do with it. I mean, at one time I had a team with a young lady in it who couldn't be bothered studying architecture, so she went into computers. I had a person who'd failed to get into the Royal College of Music because although he could play the flute well, his piano playing wasn't very good. I had another woman who'd been an office manageress. And one of the best people we had at dealing with software was a fully qualified Revlon manicurist. But they could all relate to a certain extent, to the people problem that they were trying to solve, not the nitty-gritty.
Yeah. And I've seen a lot of that as well, and it irritates the IEEE Computer Society, no way. But I think this phenomenon has been with us long enough that it is not, in fact, something that marks us as a lesser field. That it's part of the process. And the 3 points that I laid it down, the common definition, well, it's Anthony Giddens, definitions of modernity. You know, understanding production, understanding urban life where you have to concentrate labor for production, understanding how you write rules for organizations to make decisions so that they do things fairly in managing urban life and production. That requires a lot of ground knowledge. And the point that you're hiring people who have that ground knowledge. And there certainly is going to be an industrialization of Revlon manicure, I'm sure. Well, that in itself is an industrialization because it's a brand and it's standard. But that's part of where we are in life. And I think if anything, my argument is that software engineering is part of the process by which we sustain modern life. And not only part of it, really at the core of the process we use to sustain modern life. Question?
I wanted to follow up on his comment about you'd think that this was a successful discipline.
I'm in charge of the professional society, it has to be said.
You mentioned the 60s and the 70s when everybody was talking about the software crisis.
Mm-hmm.
And at that time, and for a very long time afterwards, I used to have pinned up on above my desk a quote from one of the journals saying, "There is no software crisis." And his argument was, well, if it was that bad, we would have done something about it.
Since we've not done anything, therefore there's no crisis.
And that in some ways, the ways in which crisis software failed, software projects failed, was perhaps, unfortunately I can't remember the details of his argument, but there were positive aspects to that. And for instance, one of the positive aspects is that by trying to do something that later turns out to be impossible or very difficult, as you said, a lot of the difficulty is down to the fact that it is inherently hard. By trying to do something very difficult, you maybe don't succeed in doing what you originally intended to do, but you do advance the technology quite significantly. I mean, it's invidious to pick any particular example because you can easily shoot it down. But I mean, for instance, the national health system in Britain, where they were trying to achieve a system that integrated all of the health data about everybody into one system. Well, okay, maybe they didn't succeed in doing that, but they did succeed in producing a database which didn't do all the integration things that they wanted to do, but they did succeed in producing a database which was probably larger than any database that's been produced before or something like that. So it's just a thought that maybe, as I say, that maybe there isn't such a crisis. Maybe it's part of the way things have to be.
Right. I'm not very pleased with the word crisis because I think it misses the point. And a friend of mine, Bob Charette, who is a bomb thrower in the IEEE, wrote an article that appeared right after the one, Electric Cars, Are They Really Less Polluting? His was STEM crisis, there is no STEM crisis. And his argument was that the complaints were that you couldn't hire technical labor for the prices people wanted to pay, and hence there was a crisis. And I think there is that economic aspect to it, that people would like to pay less for technical talent. But I think there's also another point that you got at that's sort of the same thing, is that our visions can run much farther ahead than what we can accomplish. And I think everyone in this room who has done any software programming at all, even an elementary one, knows that you saw this beautiful vision at the end, and you couldn't begin to get there with the resources you have. Now, it's not always just a resource problem. Sometimes it's a knowledge problem, sometimes it's an algorithm problem, sometimes it's a structuring problem. We all have seen software that goes because it solves something that's better than nothing, but it's horribly structured, so you can't expand it. But there is certainly a vision, and how that vision fits into the world we have, and how the world we have fits in the world we want. And there we are. It's done. Yes, I was waiting for you to put your hand up. You had it up earlier. And then
yes,
you got 10
I wanted to raise a point really about sort of the more academic approach to software engineering,
right,
which seems to have gone a bit out of favour of late.
Mm-hmm.
But when I started programming back in my teens on Fortran 4 on a very old machine,
right,
as a hobby, I've done it ever since as a living.
We think of them as classic.
Oh, sorry. One of the things that struck me as I learned my way through the program development process, again almost entirely self-taught, is that the academic approach could almost completely miss the point of it. And you would have an academic approach to software development that would perfectly specify a language and how it should be used and the machine it should run on, but it wouldn't actually do anything useful like save people's names to a database that you could get back again later and that kind of thing. And I just wondered, you know, if you see that as either a draw or a drain or an influence on the way software development has gone, because certainly my experience matches your later software lifecycle, that eventually what you realise you're actually doing is studying, learning about and implementing a system, and writing the software is almost a sideline. It's studying the system that's important and understanding it in being able to cope, especially with the people things, as you've said.
Right.
And the academic approach seems to completely ignore that side of it and look only at the theoretical programming.
Well, whether it ignores it or not, there's aspects of all of life is like that old joke where you see a guy outside in the evening and he's bent over looking at the ground, and you say, "What are you doing?" He goes, "I lost my contact lens here." Lost my contact lens, and you start to help him, and you scour the ground for an hour, and you say, "You sure you lost it here?" "No, I lost it up there, but the light's better here." That joke describes so much of life. Are you trying to solve this problem? No, I'm trying to solve that problem, but this one's easier. Impossible, but easier. You know, in academic life, as you're trying to develop a certain set of skills, just the process of it, you put boxes around it and remove complexities, which are exactly the ones you mentioned. I'm right now overseeing the master's project, so if you're viewing this on home, all the students remember the deadline is still Friday. Internet works here too. That I tell the students at the start, this is exactly like real life, but we make some compromises. And in fact, we make lots of compromises. The biggest one is it's a semester project. That's the box. We can't go over it. You've got to finish your project. And there are a bunch of other compromises that as you work with them throughout the term, you make it very clear, we have made this. You're not solving a real world problem. You're solving a puzzle we have set up. And we have put some, I don't know why this is current in America, lipstick on the pig, to make it look like a real problem. But in fact, it's a puzzle that we have created to develop some skill for you. And I think that carries over, and we fool ourselves to thinking that this is in fact real world, and in fact, it's a puzzle. In engineering schools, we have a joke that the C students hire the B students, and they all become millionaires, and the A students become professors, and sit back and become embittered at their loss of fortune. The students, the people who are good at software development, have a much broader sense of skill. And in recent years, I've been spending a lot of time in business incubators, watching new companies work on them, and realizing that the skills that the young men and women have who are doing this are vaguely related to academic skills. They certainly have the same names, but they would not succeed in academic life. And the complexity that they deal with requires something more than the in-depth knowledge that we would impart to them in class. And I think I've seen the death of business schools. I think I've seen a certain amount of the death of coding schools. That we're going to do in other ways because to solve these problems, you do need that wider skill. And that academic can take you so far in a certain direction, but there may be other directions that get you to that point much more quickly. Okay, question in the back?
Where do you think software engineering is going in the large? I work for a large financial institution, and we now have thousands of systems that are connected together.
Yes.
Of ages now, that people thought would have gone away, but they're now 20, 30-year-old programs. And not just the COBOL ones, we've got 40-year-old ones on the mainframe.
RPG?
Probably somewhere, but I don't have to deal with it. I don't know of that one. But it wouldn't surprise me. Yeah?
No.
So where is the software engineering profession going for engineering in the large, and conservation but not as preservation?
Right. Mike, you want to answer that one? You won't tell anyone?
You're the speaker.
I'm the speaker.
You're the one we welcome to hear.
Yeah, but you're more in tune with that one. Mike's at Lero in Ireland, although you live in Washington.
It's one of those anomalies.
It's just a suburb of Dublin. From what I've seen, we're struggling with this idea, which you've hinted at, and we've hit several points of monolithic systems. And I don't remember who talked about in the back over here. Yes, I see nodding. You get full credit, sir. Congratulations for nodding first. That there's huge stuff out there that we can't handle. All we can do is fix the local system. I think we deny that that's true, because first off, we do have some large systems, maybe Microsoft released one recently that had that problem, I don't know. That we miss some of the dealing with the small, but that still leaves large problems to be solved. And in particular, some large fundamental problems. but are we properly thinking about how we factor the software out? How do we look at things that, okay, these are the big parts, this is the big complex things, but this is all we need to do as a monolithic or as a complex system. And what can we get out in a way that we can handle it in the local, we can handle it in the small, we factor it in that way. And in particular, do it in a way so that the damage it causes other parts of the ecosystem can be identified and contained. And I'm not sure we're there yet. I do things with various software groups and software institutes, and I still see, the big system being the one that we're talking about. And you need to develop that skill, because if you don't have it, well, says he who just talked about word choice. If you don't get that in one way or the other, those problems will still be there, will still be there. But are we just as, at some level to me, the period from '64 to the early '70s was recognizing that we don't have the problem of everyone maintaining their own systems. We can amortize software costs over many installations. The question of can we now rethink about it and amortize some of the risk by isolating it in the specific local area and know how to handle the risk outside, what you cause others, and the risk you import or create on your own. That's the best I can offer at the moment, because this is not really my expertise. The past is so much easier.
Very true.
Well, thank you once again. Thank you for answering the comments and questions. We've had a wonderful afternoon, so thank you.